Silent Disco started. First up today, you are here to master the art of problem solving. Please give a warm welcome to Peter Morales from New Relic.
Thanks very much, Felicity. I'm really humbled to see so many people here interested in my favorite topic, which is problem solving. Before I get started, I just want to get a lay of the land and ask, how many of you deal with incidents or respond to incidents every day? Can you please put your hand up? Very good. So I think I got the right crowd. How many of you feel like you have a repeatable process to solving incidents? You know what tools to use, you know what data you need, and you use the same process for any type of incident? Can you please put your hand up? So some thumbs down. Okay, so hopefully you get some value out of this session, because my goal is to show you an approach on how we solve problems at New Relic based on myself observing incident response teams at New Relic and also talking to our customers. So the agenda for today, I'm going to briefly talk about who we are at New Relic and what we do. I'm going to talk about the motivation for this talk, why problem solving has become a real challenge for us, particularly in modern day environments. I'm then going to show you how to do it effectively using both tools, capabilities, and experience. And lastly, I'm going to step you through a problem-solving process you could use to solve most problems in your environment. So at New Relic, we are the founders of application performance monitoring. We were founded in 2003, and today we run one of the world's largest cloud observability platforms. In a nutshell, what that means is we collect a whole bunch of telemetry data from our customers' systems, both applications, mobile apps, websites, cloud environments, you name it, point-of-sale systems. We then store that data and we do discovery on that data to understand all the dependencies across those components. Then we analyze that data for our customers. We do correlation analysis, causal analysis, we do anomaly detection, and then we visualize all that information for our customers so they can make intelligent decisions about the health and performance of their environments. Fundamentally, what we do is that we'll help our customers run reliable digital systems. Now, the motivation for this talk actually started in 2021 when I first joined New Relic. I talked to a lot of customers. I cover the APAC region, and one of the common patterns and threads that I learned talking to customers is they all had a different approach to problem solving, which is not where you want to be. You want to try and find one approach to problem solving that all engineers can use to get to the root cause of problems. And so the first thing I did is I researched the observability industry to figure out, was there a process out there already developed that people are using? And I didn't find anything that was actually very practical. If you search problem solving on the internet, you'll probably find two examples. One is the core analysis loop, and the second one is the OODA loop. And these are quite abstract, iterative methods on generalizing the problem-solving approach, but what they don't talk about is the tools, the capabilities, and the data you need to solve problems. So I was looking for something a lot more prescriptive, and so I ended up developing my own problem-solving process. And the way I did that is by observing our incident response teams and also talking to our customers. So that's what I'm going to share with you now in the next 20 or so minutes. Before I talk about the blueprint that I'm going to share with you, I just want to go and reiterate why problem solving is such a challenge now. I think this picture here illustrates on the left, the challenge we all face as IT professionals. That picture there, it's a bit blurry, but it is a distributed trace for one New Relic customer for one transaction. And this one transaction touches 158 services. It makes 558 calls, and it takes 5 seconds to complete. In addition to that complexity, this customer infrastructure is spread across 4 cloud providers. They have 17,000 databases, 24,000 microservices, and they do 10,000 deployments every day. Now, I realize that this is a massive and extreme example, but I think many of us in the room will face similar levels of complexities, just at different scales. So if we look at the specific issues around problem solving and why it's so complex today, we can boil it down to these couple points. Number one, all of our environments now are highly distributed. Many of our customers are running microservices architectures so they can meet demand based on their users' needs. Second, customers are accessing our applications 24/7, so there's never a good time to take an application down anymore. Third, developers are releasing code all the time now. At New Relic, we do about 6,000 deployments a week. You saw that last customer, they're doing 10,000 deployments a day. So if you're a systems engineer trying to figure out what's happening in your environment, you have no idea what changes are happening. And that's a massive challenge. And then lastly, when it comes to actually investigating problems, think about it. 10, 50, hundreds of dependencies that you need to follow the bouncing ball to figure out where is the root cause, right? Environments these days are become extremely complex. So this is the blueprint I'm actually going to share with you today to make you more successful at problem solving. And there's 5 key ingredients you need to do it successfully. I'm going to touch on these at a high level and then dive deep into each one of these. The first one on the top left is telemetry data. I'm going to tell you what telemetry data you need and what questions you can ask of that data and what questions you cannot ask of that data. The second thing I'm going to tell you is you're going to need diverse sources of data. If you look at a lot of different dashboards in any observability platform, you're going to see lots of correlation, lots of coincidences. And the problem with that is the only way to eliminate coincidences is to look at a problem from different angles. And you need diverse data to achieve that. The third thing I'm going to talk about is capability. You need capabilities to help you narrow down the problem very quickly, but you also need those capabilities to help you figure out who to bring in to help you solve those problems, because you might need people from different domains within your organization to solve a really complex issue. The fourth thing I'm going to tell you about is experience. If we have a lot of experience in problem solving, then we can use that experience to shortcut the decision-making process. So how do you gain that experience and how do we benefit from that experience? And the last thing is you need to put all these things together into a repeatable process that you can use to solve any type of problems, and I'm going to run you through that process as well. So let's talk about telemetry data. So everyone knows metrics, right? Metrics are aggregate measurements of events over fixed time intervals. That should give you a hint of what they're good at and what they're not good at. Metrics are good at describing broad populations. So for example, the response time of my service can be described easily by a metric. So they're good at using metrics to detect broad symptoms, right? You can detect whether a service is performing well or not. One thing you can't do with metrics is detect individual subsets of that service within that service. Metrics are also good at capacity planning and trending analysis, right? Because they can be stored efficiently for a very long time, and they are ubiquitous. Most things in infrastructure or cloud will emit some type of metric to help you understand the health and performance of that service. Metrics are have some downsides as well, right? So metrics are not good for detecting narrow symptoms. So if there's a big problem in your environment, the metric will show you that. But if there's a narrow environment that's affecting a subset of your users, typically a metric is not going to show you that that issue is occurring. And then secondly, metrics are only good at understanding known quantities that you're measuring, like CPU, memory, storage, and so forth. They don't help us understand unknown problems, right? Because you have to define a metric in advance, and if you knew all your problems in advance, then you wouldn't have any problem to solve. These are the key questions we often answer when it comes to metrics, right? Has a measurement changed recently? So what we're looking for is deviations in that metric to understand if there's a change in behavior. How does the measurement compare to a previous period? This is where we do period over period analysis to see if something looks normal or abnormal. And then the last one there is what direction is it trending in? Is it speeding up? Is it slowing down? Is it growing? Is it shrinking? The key takeaway when it comes to metrics is they help us detect broad changes in behavior. And so the key word here is broad, right? Broad symptoms. The next telemetry data type is events. And events are, what are metrics? Metrics are the aggregate of these raw events. So if we want to understand the problem deeper, we actually have to look into the event associated with that metric, all right? So the key capability of events is they capture all the detailed information. All the metadata is stored as attributes, and you can derive measurements from those events very easily. And so what are events good at? They're good at helping us measure the subpopulation. So if I wanted to know the response time for a particular class of users, I can use an event to achieve that. There are downsides to events. Because it's the raw data, they consume lots of storage space. Therefore, they are short-lived. We don't keep them around for very long. We're not going to keep events around for 7 years, right? It would just cost too much. And therefore, they are often sampled. And because they're sampled, when we derive a measurement from an event, we lose precision. And therefore, it's not an absolute measurement, right? It's an approximation. So you've got to keep that into consideration when you use events to create measurements. These are the types of questions we'll answer with events. What request was made? Where was it made? What was the result? Was it successful? Did it fail? Who made it? How long did it take? And what changed, right? The key here is you can answer very specific questions when it comes to events rather than broad questions. And so the takeaway is they help us approximate behavior at granular levels and narrow down the problem, right? So the key words there is granular. We can start to narrow in on problems. Logs, everyone loves logs. Logs are just events, right? But they're semi-structured. The value of logs is they can contain arbitrary information. There's no real data model that restricts to what you can send in a log line, right? And they're ubiquitous, meaning modern systems emit logs and legacy systems emit logs. But there's lots of problems with logs. They're unpredictable. Garbage in, garbage out. If your developers are not sending useful information, the log's not going to tell you anything, right? Second, they consume huge amounts of storage, huge amounts of network, and therefore they're often slow to search, and your time to glass is also very slow. So most investigations never start with logs. But I'm sure that some of you still do that. These are the value you get out of logs. They tell us what led up to an event and what happened after an event. So we have that chronological order of what happened leading up to a symptom. That's the real value of logs. And assuming your developers are logging useful information, they tell us the why. Why did a problem occur? The last data type is distributed tracing. Distributed tracing is essentially, all it is connected events. They tell us what path did a transaction take throughout our application stack. And the value is that you get the causal relationship between your services. So you're no longer relying on correlation and metrics. Distributed tracing will tell you that this service talked to this service, which talked to this service, and that's guaranteed. Okay? And similar to events, they log detailed information. People don't talk about downsides to distributed traces. There is one significant downside, is that they're brittle. That example I shared in the beginning where we had 158 services, to get that call graph, all those 158 services have to be instrumented. And that's often spread across different teams, and that's not always easy to get those teams to do instrumentation. So when you can't get all the teams to do distributed tracing, you end up with lots of dead ends in that call graph, and no one trusts it anymore. Okay, so that's the downside. Other downsides, retention is short-lived because they do consume lots of space. And again, to supplement that, they're often sampled, and therefore the measurement, you lose precision, right? So you only end up with approximations, which can be a problem when you're trying to identify the long tail in your distribution. These are the questions we often ask with distributed traces. What path did a request take? Which step is taking longer than usual? What errors were emitted? And are errors elevated for a particular transaction, right? So you're trying to pinpoint within that call graph where things are going wrong, where things are slowing down. The takeaway for traces is they help you track down the source of problems. So they help you follow that bouncing ball when the problem is not obvious, right? If you've got a simple architecture, you probably can get away without distributed traces, but if you've got a complicated architecture, you can't live without distributed traces. So that's it for telemetry data. The key takeaway here is they're all four are complementary. You actually need all four because they help you answer different questions. And one is not a good substitute for another. The second thing I want to talk about here is having diverse sources of data, and I want to emphasize the word here, diverse. So this is a typical application stack, right? 3 layers. You've got your end user layer. That's where your users interact with your application, your mobile, your website. You've got your business logic layer, services in the middle, and then you've got your resources that your application is consuming. It's very important to observe the end user layer for 2 reasons. There's too many devices out there. There's a lot of diversity in devices. It's impossible to test all combinations. The second reason is a lot of applications now are making external API calls to services that you don't control. So the only way you can understand whether those APIs are working is to be observing at the end user layer. The services layer is obviously very important to observe, because that's your business logic, that's your code. Every time you release, you want to make sure that behaviors haven't changed. And resources layer also very important to observe, because resources are finite. As much as everyone here is still doing auto scaling, the reality is even auto scaling has its limits. So we need to understand when we exhaust our resources. Now, the common question I get now is, that's a lot of observability I have to do there. It's going to be really expensive. Do I have to observe all the layers? And the short answer is yes. And the reason is very simple. This is my analogy of the leaky bucket, right? We have a bucket, the root cause is in the bucket. Each time you decide not to instrument or observe something, what ends up happening is we put a hole in the bucket. And the less you observe, the more holes are in that bucket. And what does that mean? Is the root cause leaks out, and therefore you are not able to explain the reason for the incident, right? And that incident will therefore repeat itself. And this is the most common problem I see across all customers and across the industry as a whole, is we take shortcuts when it comes to full stack observability, and therefore those incidents keep repeating themselves because we cannot get to the root cause. The third is we need capability. I'm going to talk about 4 key capabilities that will help you narrow down the problem. These are capabilities in New Relic, but you should be able to look for similar capabilities in your observability platform as well. The first is what we call at New Relic workloads. And workloads, all it is a construct that allows us to group related components and objects together, so we can look at the health of an environment holistically. So for example, if you're a retailer and you've got an online retail store, we will group all the mobile app, the website, all the back-end services and all the infrastructure associated with it into a workload. And that will tell us at a glance straight away what is the health of that workload. And more importantly, during an incident, it will show you what is the impact radius and how it's unfolding in real time, right? And then thirdly, we see all the dependencies. We have the entire dependency tree associated with my online retail store, and I can see how things are connected. And then last, we have a timeline of events. So we can see for every component in that workload, what happened leading up to the symptom or the actual problem. Maybe there were certain alerts, maybe there were other issues. The timeline of events, or maybe there were changes. The timeline of events will tell me that straight away. The fundamental goal of having a workload is be able to understand what is the scope of the problem and where you should start investigating. And it will fundamentally reduce your mean time to understanding the problem. The next one is distributed tracing. This is a quote from Kai-Su Lee, a Google SRE. He said, "You can find the needle in the haystack if you thread the needle through the stack with a propagation tag." And that's exactly what happens with distributed tracing. We tag the transaction and we follow that transaction and as it goes through all the different services. And that's how we create that dependency and that call graph. And what that allows us to do is do period over period comparisons. So we can say this particular transaction is taking longer than usual, or maybe it's slowing down in this particular section of the code. Distributed tracing will unveil all that information for you. And also it will show you where your services are actually emitting errors and impacting that particular transaction. If you are running distributed systems, it's mandatory to have distributed tracing. The third one is change tracking. Change is a big source of problems when it comes to problem solving. So we want some way to visualize changes when we're looking at charts and dashboards within our observability platform. In New Relic, our customers send us what we call change markers to describe notable events. It could be an infrastructure change, configuration change. It could be a feature flag progression, let's say 10%, 20%, so forth. Or it could be a marketing campaign. So marketing's running this big campaign and we expect a boost in volumes, right? What we do is overlay these change markers across all our charts and our dashboards so you can see what was the impact of that change on all the different telemetry data and all the different metrics. And you can see it straight away in real time. It's actually a very important feature. And then the last one is you need some type of intelligence features to sort of guide you on where you should look, where you should start looking at the problem. Typically when it comes to intelligence features, there's two things that vendors develop. One is anomaly detection and the other is some kind of causal analysis. I will say the biggest problem with all intelligence features is garbage in, garbage out, right? If you don't feed these intelligence features diverse data, they will not be able to triangulate the problem for you. So having diverse data and feeding it into your platform is actually going to be very significant for these intelligence features to actually work. You also need experience. How do we learn from people in the past, right? If you don't have lots of experienced engineers on your teams, the good news is there's a lot of information in the public domain about incidents, causal analysis and problem solving. This is actually a paper from New Relic, not from New Relic, from Microsoft, titled What Bugs Cause Production Cloud Incidents. And what they did is they classified production issues in Microsoft Azure over 6 months. So that helps them with the decision-making process. What they found is 31% of all incidents were due to software faults and 21% due to data format bugs. And all those issues were introduced because of change. The other thing they found is most software incidents resolved through a mitigation strategy like rolling back code. Another paper, why do internet services fail and what can be done about it? The leading cause of service failure for this was operator error, and more than half of those errors were from bad configurations. What can we take away from this? There's two things we can take away. When you're triaging a problem, the first thing you should look for is changes. The second thing you should look for is errors. If you do those two things, then you should be able to solve 50% of your problems fairly quickly, assuming the same conditions. All right, so I've just told you a whole lot about all the things you need to problem solve. Now I'm going to show you the process that we use internally to solve problems at New Relic. This is a little bit of an eye chart, but this is designed to be generalized to any type of observability or monitoring solution that you use. On the left, you actually have the problem-solving steps that you need to follow. On the right, you have the data and the sources of data that you need to solve problems. The one caveat here is I've left out the end-user layer because I couldn't fit it in the chart. But hopefully you'll get the idea. So all problems start with symptoms, right? And symptoms can be reported in different ways. Customer complaints through service desk. It could be your alerting pipeline. It could be anomalies, threshold-based alerts, alerts on your error budgets. It could be your synthetic probes alerting about availability. Or it could be an engineer looking at dashboards, seeing a deviation in metrics and thinking, what's going on there? I need to understand and investigate that. A symptom will fundamentally be highlighting a service or a service having an issue within your environment. And this is where I would use workloads to figure out which services are having an issue, and therefore out of that set of services, which one should I actually start investigating first? And this is where you need to use a little bit of intuition. What I typically do is I start with investigating the service that has the most dependencies. Because if you think about a call graph, most problems go deep and then they surface themselves back up to the edge of that call graph. So you want to go as deep as possible and investigate the deepest service first. Okay? And you might be able to spot that using service maps if you have that capability. The next question we want to ask is what's changed? Right? So for that particular service, you want to ask the first question is, has there anything changed associated with that service or any services it depends on? right? And this is where change tracking becomes fundamentally important capability, because you can ask that question straight away. If there's been no changes, then we go to the next step. And the next step is we ask about errors. Most services emit some constant level of errors. So what we're not looking for actual errors. What we're looking for is a change in behavior associated with errors, right? An increase, a decrease in error counts. And so we want to rule errors out quickly, because as we saw from the research, they're a common source of problems within environments. And if we do find an error, then we actually want to look at logs to help us explain why did that error actually occur associated with that service. If there are no errors, the next step is we want to rule out local dependencies. Local dependencies are things like anything that service consumes locally, such as the infrastructure, right? CPU, memory, network, storage, etc. And this is where we would typically use metrics and period over period comparison to understand whether those local dependencies are behaving normally or abnormally, right? If they're behaving abnormally, then you have a lead to follow. If they're behaving normally, then we go to the next step. The next step is to rule out remote dependencies. There can be lots of remote dependencies, depends on your app. The two I typically start with is databases, because databases are often volatile because of I/O, particularly if you don't have provisioned IOPS. And also there's always limits when it comes to connection pools. And then the second thing I look at is external services, right? What external services is my service consuming? Because those services are not in my control, and therefore I need to understand whether they're healthy and whether they're performant. If there are no issues with remote dependencies, then the next step is you actually have to now narrow in on the problem. So far we've been looking at it broadly from a service perspective, but now we actually need to look at what transactions is that particular service supporting, and look at a transaction level and see if we can find a set of transactions that are actually having change in behavior, okay? And if we do find a particular set of transactions that has a change in behavior, that's when we use distributed tracing to follow the bouncing ball associated with that set of transactions. And that will then tell us what is the next suspicious service that I need to investigate. And therefore we go back up and follow the loop again. And we keep doing this until we get to the root cause. Okay? So that's the process. I know it's quite detailed, but it's actually by design, because it's meant to generalize to a lot of different situations. Having said that, as you saw, right, problem solving, it's by no means easy. It's become a lot harder, but I believe if you use this blueprint, it's going to help you master problem solving in the future. With that, if you're interested in learning more, please come and see us at the New Relic booth, and we can talk more, and please check out our platform. And if anyone wants to connect, they can find me on LinkedIn. Thank you very much.
So just a quick thing, please don't forget to download the AWS Summit app and provide your feedback for every session today. If you're leaving the room, please have your badge out ready to scan out. You'll be scanning out and in of every room today. The next session coming up is building self-healing code with generative AI on AWS. It is expert level 400, so stay in this room. If you're up for that session, you're in for a treat. Thank you all.